Hello everyone, welcome to the second lecture of 5th week of the course Process Equipment Design, and this is 22nd lecture of this course, and here we are going to start discussion on condenser. And so first of all we will discuss different types of condensers and its uses, and then we will start design of condensers, right. So this complete topic I will cover in 3 lectures, like lecture 2, lecture 3 and lecture 4 of 5th week. Okay. So let us start discussion on condenser. So first of all, what is a condenser? If I ask you, being a chemical engineer, you all know that condenser is a device or an equipment where we convert vapor into liquid, right, and so it transfer its latent heat to another fluid, fine. So that is basically the condenser. Now if I ask you that in which case, now if I ask you what are the utilities or what are the applications of the condenser, so you can see that condensers are used in variety of operations in chemical and petrochemical processes, which include distillation, refrigeration and power generation. Okay. So I hope you all are aware with the application of condenser in different industries or different processes, as we have already discussed, right. So as far as distillation is concerned, virtually every distillation column employs either a partial or total condenser, okay, and in that way it converts vapor into liquid, okay. And if you understand the placement of condenser in distillation column, it is basically placed at the top of the distillation column, where whatever vapor is generated in distillation column, it is converted into liquid, okay. And what will happen after that? Some section of that liquid recycles back to the distillation column, and which we call as a reflux, right. And at the same time, some section of the condenser exits as a product, or we can call it as a top product, okay. Now if I ask you that what is a total condenser and what is a partial condenser, okay, I hope you know that, but let me further explain it to you, okay. So as far as partial and total condenser is concerned, it entirely depends on what phase of product you want, right, what phase of product you want from distillation column as top product, okay. So what will happen when I say that your product should be in vapor form, okay. So what you can consider, that whatever vapor you can take as a, so what you can do over here, you can consider whatever vapor is exiting the distillation column, that you can consider as a product, right. But no, because what will happen if I ask you that you should consider product in vapor form, okay, but then also you require some liquid, because that liquid should return to the distillation column as a reflux, because unless I am not having vapor and liquid phases in distillation column, the process cannot be carried out, right. So if I ask you that your top product should be a vapor, okay, then only the vapor which is exiting from the distillation column, it should enter into the condenser, and some section of that vapor should be converted into liquid, and that liquid should return back to the distillation column as reflux, right. And in that case, vapor you can obtain as product. So what you have done, you have obtained your product in vapor form, but at the same time you have returned the liquid to distillation column as reflux. So whatever feed is entering into the condenser, only some section of that vapor is converted into liquid, and that will depend on how much reflux you want, right. So, in that case some of the section of vapor is converted into the liquid, and therefore, you call that as partial condenser, right. Now, if I ask you what should be the total condenser? Total condenser basically condense complete vapor which is entering into this, and in that case reflux as well as top product of the distillation column both should be at liquid phase. So, in that case we consider that as total condenser, and if product I want as vapor we consider partial condenser. So, I hope you understand the difference between the two. And as we have already discussed that condenser use in refrigeration operation is very important. Okay. So, in refrigeration operation condensers are used to liquefy the high pressure refrigerant vapor leaving the compressor. Okay. So, if you recall the refrigeration cycle, what will happen? Initially we have evaporator. Okay. In that evaporator, whatever liquid and vapor mixture is entering from throttle valve, okay, that liquid is converted into the vapor, and complete vapor further enters into the compressor where it is reaching to high pressure and high temperature, and then it is further entering into the condenser where the vapor gives its heat to the atmosphere. Okay. And then after that we have vapor, and then after that vapor is converted into the liquid, and that liquid is further entered into the throttle valve where sudden expansion gives vapor as well as liquid, and that vapor liquid mixture is again into the evaporator. So, you see we have evaporator, compressor, condenser and throttle valve. Okay. This is basically the refrigeration cycle, and based on that refrigeration and based on that refrigerators which we are use in our houses, it also works, right. So, here we use the condenser extensively. Okay. And after that we can use the condenser in power generation. Okay. Now, what will happen in power generation? Or let me ask you what will happen in Rankine cycle, because thermal power plant works on Rankine cycle, because thermal power plant works on Rankine cycle principle, right. So, first of all water is basically preheated and then converted into saturated steam in boiler, and after that it is converted into supersaturated condition, and after that it is converted into supersaturated form, and then it is entered into steam turbine where expansion of vapor takes place. Due to that expansion in steam turbine, shaft moves and we can have electricity, right. But what will happen with that steam? Steam is condensed when it come across the turbine, right, but complete steam is not condensed, some vapor will remain there. Okay. So, what will happen after that? That vapor liquid mixture enters into the condenser, okay, and whatever vapor is available there, that is further converted into liquid, and after that whatever liquid is generated, it is further entering into the boiler. Okay. So, what will happen over here? Here whatever vapor is available in partial form, because some vapor is there, some liquid is there, that is converted into complete liquid, okay, in condenser. Now, can I directly send this to reboil? Now, can I directly send this to boiler? The answer is no, because what will happen? We have vapor and liquid mixture, right, and when we pump it, okay, it will damage the pump, or pump will not work, okay, when vapor will be there. So, in that case we have to ensure that feed to the pump is complete liquid, and to ensure that we use condenser where all vapor is converted into the liquid and then it pumps to the boiler, right. So, in this way we can use condenser in distillation column, in refrigeration cycle and Rankine cycle, that is the power generation cycle. Okay. So, these are some of the uses of condenser. Now let us further discuss few facts about condenser. Okay. So, you see condensation is a reverse of boiling. Okay. Boiling we generate vapor and in condenser we generate liquid, and the condensing curve is the same as the boiling curve. Thus, many of the computational difficulties encountered in the analysis of reboilers are present in condenser as well, because both activity are just opposite to each other, right, if I consider reboiler and if I consider condenser. Okay. So, for wide boiling mixture in particular, the non-linearity of condensing vapor and the variation of liquid and vapor properties over the condensing range mean that a zone or incremental analysis is required for rigorous calculation. So, you see here we have considered reboiler and condenser just opposite to each other, and what difficulty we can obtain, because it is not the easy method, because it is not an easy phenomena and some rigorous calculation should be required. Okay. Why we require design of the condenser? Because its use in chemical industry is extensive, which we have already discussed. Okay. Now, most of the condenser which are used in chemical plant are shell and tube type. Okay. And in some cases we also use air cooled exchangers. Okay. So, these are specifically shell and tube types as well as air cooled exchanger. Air cooled exchanger we have already discussed in detail when we have discussed classification of exchanger. Okay. So, that lecture you can refer to understand air cooled exchangers properly. Now, what will happen with air cooled exchanger? In copper tube we have vapor which is to be condensed, and over that in cross manner we inject air. Okay. So, instead of some cooling liquid media, we use air to condense the vapor. Okay. So, you can understand in air cooled heat exchangers we usually use fan which is used as a coolant. We usually use fan in which air is used as a coolant instead of water in shell and tube heat exchanger, right. So, what we can observe over here, that most of the exchangers are shell and tube type, and apart from that other type of exchangers are also used, but its use as a condenser is not significant. Okay. However, other type of equipment such as double pipe heat exchanger, plate and frame exchanger and direct contact condensers are less frequently used. However, it is used, but use is not extensive. In direct contact condensing, coolant is sprayed directly into the condensing vapor. So, you can understand that apart from shell and tube heat exchanger, we have other exchangers also which are used as condenser, but not as frequently as shell and tube heat exchanger, right. So, now discuss the types of shell and tube condenser, because we are going to design the shell and tube condensers only. So, we will discuss type of these condensers only. So, if you focus on the construction of a condenser, it is similar to shell and tube heat exchanger, but with some modifications. Okay. What is the modification? Here I am using wider baffle spacing. Okay. So, in this case baffle spacing should be equal to ds. Now, here we will not follow the guideline for baffle spacing, that baffle spacing should be equal to 0.221 into shell dia. Here we will consider baffle spacing equal to shell dia, right. When I am considering condensation in shell side, if condensation is in tube side, shell side should be designed normally, okay. But here baffle spacing should be wider, and the reason is because we are considering vapor, and vapor movement is not up and down as usually we have when the liquid stream is used in shell and tube exchange, when liquid stream is used in shell and tube exchanger, right. So, in this case vapor move, and vapor should require wider space to move, okay, and therefore baffle spacing over here is equal to shell dia, and that is very wide. I hope you can imagine that. So, now let me classify the condenser, and usually we have 4 types of condenser, and these are shell and tube types, okay. And as far as classification is concerned, this is based on 2 factor. Number 1, based on orientation, okay, how it is placed. Second is where condensation is going on, okay. Now, if I ask you where the condensation should be going on in shell and tube condenser, you have only 2 answer, either shell side or tube side, right. You have only 2 options, either shell side or tube side, right. Now, if I ask you what is the orientation of condenser, so in that case you again should have 2 options only, one is vertical and second is horizontal, right. So, only 4 condenser we can configure depending upon orientation and the side of condensation, and these 4 condensers are horizontal condenser where condensation is in shell side, okay, and cooling media is available in tube, okay. Second is horizontal condenser where condensation is in shell side. Second is horizontal condenser where condensation is in tube side, okay. In the similar line, vertical condenser where condensation is in shell side, and vertical condenser where condensation is in tube side. So, we have 4 configuration as you can observe here, okay. So, now we will see each type of condenser in detail. So, let us start with horizontal shell side condenser. So, in most of the process industries, these type of condensers are used in order to minimize the cost of support structure and facilitate maintenance operations, okay. So, what is the meaning of that? If your condenser is having larger duty, right. If your condenser has larger duty, it is better to place that condenser horizontally, because when I am placing the condenser horizontally, I can provide better support in comparison to I am providing or I am placing large duty condenser vertically, because for vertical equipment support structure is very important, okay, and that is not as easy as it is, for horizontal condenser, right. So, if duty of condenser is larger, we should place that condenser horizontally, okay, and it will ease the maintenance problem also. How? Because when you have larger condenser and which is placed horizontally, you can take the bundle out very easily, right, when it is placed horizontally. However, when it is placed vertically, the removal of bundle from shell is very difficult, though that can be done, but when we compare the easiness of the maintenance, it is more easy in horizontal condenser, okay. So, you should keep in mind how you decide the placement of the condenser, it will depend on larger duty, okay. If duty is small, you can place vertically, no problem, okay. So, here we have horizontal shell side condenser, and if I am saying that shell side condenser, it means vapor should enter into shell side and the cooling media should enter into tube side, okay. So, in this case condensing vapor is often an organic compound or a mixture, and the coolant is most often as water, okay. So, condensing vapor is most frequently placed in shell side, okay, and cooling media, which is the water, is usually more prone to fouling and therefore it should be allocated to tube side. Okay. So, shell side condensation, vapor should enter into shell side, right. So now discuss few more points about horizontal shell side condenser, and here we usually consider E shell. Okay. So, TEMA E shell is considered over here, and it is widely used in a condenser and the least expensive type of horizontal condenser. So, that you can understand, because TEMA E is the simplest type of shell. TEMA E is the simplest type of shell, so that becomes inexpensive also in comparison to others, okay, and therefore it is widely used in condenser. Next is, it may have floating head or fixed tube sheet, and baffles are usually cut vertically for side to side flow and notched at the bottom to facilitate drainage of the condensate. Okay. Now, let us consider this as when I am having a condenser in shell side. Okay. So, what will happen at top of the tube, condensate continuously form and moves downward, right. So, at the bottom condensate will be collected. Okay. Now, in such type of condenser where condensation is taking place in shell side, we usually have vertical cut in baffle. Okay. Till now what you have seen as far as baffle is concerned, usually we have this type of baffles, right. So, movement of liquid is like this. Okay. So, we can consider this type of movement in liquid. However, when I am considering vapor, okay, vapor has lesser density in comparison to liquid. So, it will never come down. Okay. It will occupy the space, but it will not come down. Okay. So, in that case, instead of horizontal cut, we usually consider vertical cut, so that vapor can move like this. Okay. I hope it is clear to you, vapor should move like this, okay, not like this, okay, as I have just shown. So, in this case, usually vertical cut is placed in baffle and it looks like this. Now, what will happen, because horizontal cut is not there. So, whatever condensate is collected at the bottom, it will remain in the exchanger, okay, it will remain in the condenser. Now, what will happen, when the condensate will be available in shell side, what will happen, some of the tubes will be merged in that condensate. I hope you understand. Okay. And when it will be merged in a condensate, those tubes will not participate in condensation process anymore until unless condensate should not be removed. So, how we can remove the condensate when baffles are having vertical cut? For that, we usually place a V notch, okay, V notch at the bottom of the condensate, and from this open space condensate is continuously removing, right. So, we can have removal of the condensate as well as the movement of vapor. Okay. So, you should keep in mind, horizontal shell side condenser, vertical cut baffle is used with a notch at the bottom for drainage of the condensate, right. And further, we can have one extra nozzle at the top of the shell, which is used as a vent to remove non-condensable gases. Okay. So, let me explain this further with the help of schematic. So, here we have the condenser, okay, and here vapor is entering into the shell side, and if you see, in this case baffle should be like this. Okay, baffle should be like this, okay, because we have vertical cut in baffles. Okay. So, vapor is entering into the shell side, and from here at the bottom we have condensate removal continuously. Okay. Now, what we have discussed previously, that it has one extra nozzle and that we call as vent. Okay. So, that you can see here I am having a vent which is just at the which is just at the end of the exchanger. Okay. If vapor is entering from one end, at another end vent should be there. Okay. So, what is the purpose of this vent? Now, if I ask you that if operation is not going on in a condenser, okay, then what will happen? The condenser will remain empty? The answer is no, because air must be there, right, and you understand that air is non-condensable gas in nature. Okay. Now, what will happen when the vapor will enter into the condenser and air will not be removed, that air will occupy some of the space in condenser, okay, which will reduce the heat transfer area which is available for condensation. So, when I am using the vapor, okay, when I am using the vapor in such equipment, we must have one extra valve and that we call as vent. Okay. Now, what will happen from this side? When vapor is entering, it is continuously moving in this side, right. So, whatever air is available in this, whatever air is available in this, it will move to this direction, okay, because from back side vapor is coming. Now, as we open this valve, at the same time vent valve should also be opened. Okay. So, as vapor will keep on entering from this, non-condensable gases will keep on leaving from vent side. Now, what will happen after when this vapor occupies the whole space? It means that non-condensable gases have been removed from the system. Okay. And how we will ensure that? That when this valve will keep on, when this valve remain open, after some time whatever vapor is entering, it will start moving from this nozzle or from this valve. So, in that case, when vapor is starting, now in this case when vapor starts exiting from the nozzle or from the vent valve, we can say that air is completely removed from the system, and at that time we close that vent, right. So, in this way we remove all non-condensable gases from the condenser. Even it is not used only in condenser, wherever I am using vapor, either it is a condenser, it is a reboiler, it is a boiler, wherever I am using vapor or steam, in that case we consider vent as well. Okay. And second point is what we do with this condensate. Okay. Because when condensate will exit, when the wall of condensate remain open, okay, and when the operation is going on, condensate will keep on exiting from the system, right. And because vapor is also there, so there are chances that vapor should also exit the system from condensate valve. Okay. So, to stop vapor into the system and to let condensate exit the system, we use another assembly which we call as steam trap, which basically traps the steam or vapor. Okay. So, in that case, when I consider, let us say condensate is exiting from here along with vapor, because you cannot stop vapor to moving out. Okay. So, it will enter into this steam trap, which is this type of structure, okay, and from here we have the exit nozzle for condensate. Now, what will happen? Usually this is closed with a valve and that valve is connected with a balloon. Okay. This type of balloon is there, and when I am having vapor and liquid mixture which is entering into this, so we have vapor as well as condensate. So, what will happen? Because of the density difference, condensate settles down, right. So condensate will start filling this space. Okay. So as condensate will start filling this space, it will let this balloon to move up, okay, because this balloon is very light. So as this balloon moves up, it will open this channel, okay, and when it will be opened, condensate will keep on exiting from here. However, it will not allow any vapor to exit, because vapor is available in this region, not in this region, because of the density difference. So in that way steam trap works, and we trap the steam or we trap the vapor and let the condensate to exit the system. Okay. So whenever I am using vapor and steam, I should use extra assembly in terms of vent nozzle and in terms of steam trap. So I hope you understand the function of vent and steam trap. And further we can consider horizontal shell side condenser as it is shown in this schematic, where vapor is entering from two side, okay, and though vapor is entering from two side, vent is available at the center, okay, because vent is must wherever I am having the vapor. Okay. So it is entering into the shell side, and baffle are usually having a vertical cut, that we have already discussed. So this type of shell where vapor is entering from two side and condensate is exiting from one side, this we call as split flow or J type shell. Okay. So in horizontal shell side condenser we usually, so in horizontal shell side condenser mostly we use TEMA E shell, but sometimes we also use TEMA J shell, as it is shown in this image. Okay. So I am stopping this lecture here only, and I will continue the types of shell and tube condenser and design in next lectures. So that is all for now. Thank you.